We now continue in this lecture with the analysis of the short circuited generator. In the previous class, we just started upon what happens when you have the synchronous machine running at a constant speed under open circuit conditions, and we apply a step voltage at the field winding. Okay. The voltage which we apply at the field winding is such that under open circuited conditions, we will get 1 per unit line to line RMS voltage at the terminals of the stator, assuming of course that the stator is connected as a star is connected in star. Now, we did not actually complete that part of the exercise. I had written a small Scilab program to see the transient behavior of an open circuited generator. So, we continue with our discussion of an open circuited generator. By the end of this lecture, we would have come to the short circuited generator and the transient response of a synchronous machine which is short circuited. So, actually what we will be doing is studying two transients. We will assume the machine is rotating at a the synchronous speed, then we give a step change in the field voltage so that the voltage builds up in a generator, the generator gets excited, and then we short circuit the generator and see the transients which arise due to that. Now, in this particular study, we will of course not be considering the interaction with the mechanical system. We will assume that the machine is running at a constant speed. We will assume it is running at the rated or the base speed. Of course, as we shall see later, under short circuit conditions, a non-zero torque is created whenever we apply a short circuit. So, in fact, the speed will be affected in a certain way, but for the time being we do not consider that that interaction with the mechanical system. We will of course do that later in this course. In fact, a large part of our course will be dedicated to studying electromechanical oscillations, which we shall see later. If you look at the synchronous machine equations, in fact just the flux equations, since we are not considering the mechanical equation or the torque equations, the flux equations are in fact linear, and these transients in fact can be studied by a simple linear system analysis, that is using eigenvalues, eigenvectors, and the complete response can be characterized and we can plot the response. We do not have to do a numerical integration because this is a linear system and the response of the system comes out to be in a nice closed form. Okay. So, that was what we discussed in the previous class. We just revised what we did then. We have got the equations of the flux of the machine under constant speed. It turns out that A1, A2, B2 will be constant matrices. EFD is a step of 1 per unit. Recall that EFD is proportional to the field voltage. In fact, we apply the field voltage so that we will have EFD as 1 per unit, or in other words, in steady state we will have the line to line voltage of a star connected synchronous generator to be 1 per unit. Okay. So, that is the voltage we applied the field. Recall that we have formulated our model in such a way that we do not really specify the field voltage, but we directly, but we say we give the field voltage in terms of what effect it has on the open circuit voltage in steady state. So, again let me repeat that we apply a field voltage such that EFD is 1, or the open circuited line to line RMS voltage of the synchronous machine is star connected is 1 per unit. Okay. So, we assume of course that the speed is constant, and we order the states in this fashion. ID and IQ, in fact, you may wonder where is VD and VQ here. VD and VQ are the voltages at the terminal of the generator. What we assume of course is that the terminal voltage of the generator is written in terms of the current ID and IQ, and since we are considering the open circuited case, we will assume that RL is a very large, we will take RL as very large. So, open circuited generator is represented as a star connected load with the resistance values RL as very large. Okay. Now, so in some sense, the effect of VD and this VD and VQ is got subsumed into A2, since we are expressed it in terms of ID and IQ. A1 looks like this. We did it in the previous class. Okay. Omega is the speed of the machine. We'll assume that in the study this speed is constant and equal to omega base, or the rated value of the synchronous generator. ID and IQ in fact are related to the fluxes, as I shown some time back, the fluxes by a matrix of this kind. Remember that this model is a per unit model. We are talking in terms of XD dash, XQ dash, but remember that earlier we were talking in terms of LD dash and LD double dash. In per unit, LD dash, LD double dash is equivalent to XD dash and XD double dash, okay, and so on. So just remember that this is a per unit model, okay. B2 of course is this. Remember we are using model 2 with the assumption that TDC double dash is equal to TD double dash. The data for this generator, I'll just show it to you on a slide. So the data for this is given in this slide. We'll be using model 2 of course, and TD0 dash will of course take us 5 seconds, not 8 seconds as given before. Now what we will do is of course kind of write a program to plot the values of the transients seen in the voltages, currents and so on for this particular transient. So the transient we are considering is a step change in the field voltage, okay. We will of course do the short circuit subsequently. So right now we will of course do the step change in field voltage. Recall that once we have got the equations of the machine in this form, which is a purely state space form, psi dot is equal to A into psi plus B2 into EFT. Remember that I is nothing but A3 into psi. So finally we get this psi dot is equal to A psi plus B2. This is a typical input output state space form of the machine equations, and we saw in the previous class that you could get the analytical expression for the response in this fashion, and that really boils down to evaluating this expression here. So we don't do a numerical integration because it's not necessary. We have got a closed form expression. We'll plug in the values of time in order to obtain the final response, okay. In this particular expression, P is in fact the eigenvector, right eigenvector matrix, which you have talked in the first the first 10 lectures of this course. We have discussed analysis method for dynamical systems, where I defined the right eigenvector, okay. And this matrix here is a diagonal matrix, okay. In fact, there are in A's of 6 by 6 matrix. So actually in this case you will have 6 eigenvalues, not 3 as shown here, okay. And this is defined in this fashion. So this is where we were last time. What we will do now is, of course, I'll show you the program corresponding to this particular transient. So I have programmed this of course using Scilab, and we had seen the program in the previous class. We'll just have a look at it fast again and then run it, okay. So let's go to that program. So we are at the Scilab workspace at the present time. I'll show you the program. It's called step.sci. We had seen it last time. We'll just run through it again quickly. So I have entered the data. It's quite intuitive and easy to follow. I'll just rerun it again. Read through it. Of course, we have given the standard parameters here. We have been given the reactances as well as the time constants. We have been given what are known as the open circuit time constants. Why these are called open circuit time constants will become apparent soon. Of course, the way we have formulated our equations, we have formulated them in terms of the time constant Td dash, Td double dash, etc. But remember, you can get Td dash and Td double dash using these two equations. Okay. In fact, you get a quadratic which we have to solve in order to get Td dash and Td double dash, and similarly Tq dash and Tq double dash. So that is what is shown on the screen at present. From the parameters, we are in fact obtaining Td dash and Td double dash. Similarly, Tq dash and Tq double dash. We have of course taken the states in this fashion, and we take RL to be a very large value in order to mimic open circuit conditions, and this is the A matrix, this is the A2 matrix, this is the B2 matrix, this is the A3 matrix, this is the final state space matrix is A. The command VD is equal to spec of A is in fact will obtain the eigenvalues and eigenvectors of A. The final steady state value of the states can be obtained by setting psi dot is equal to 0, in which case of course the steady state value of the fluxes are given by A inverse B2, which is implemented in this program here. I will just see if I can move this slightly. So now we evaluate the time response of the states. So actually it is a direct evaluation, it is not a numerical integration, because it is not necessary to numerically integrate to obtain the answers. We will assume the initial conditions before we apply the step are 0, and we actually evaluate the expression which I had just given some time back. Finally, of course, I can get, once I get the fluxes which are x denoted by x here, I can obtain the currents and the voltages and the torques and so on. Okay. So, in fact, we will plot the values of torque and the voltages etc. shortly. So, I will minimize this, and now I will actually run the program. So, what I will do is run the program from the Scilab workspace. And so in fact we are simulating it for more than 30 around 30 seconds. We shall see why we need to simulate this for 30 seconds. So it is taking a bit of time because I have evaluating it at a relatively short time interval. I mean if you look at the time I am evaluating this for. So, I will just go down, scroll down the program, and I am evaluating it every 5 milliseconds for 30 seconds. Okay. So, because of that the program did take it did take a while for it to simulate it, in fact not simulate it, evaluate it at various time instants. Now, the thing is, before I go on and show you how the time response looks like, what we first will see are the eigenvalues of the matrix A. In fact, if you try to evaluate the eigenvalues, we are getting two large numbers. These large numbers are indicative of something happening very fast. Okay. In fact, these arise because we have chosen RL to be a very large number. So, in fact, RL being a very large number results in a very large negative eigenvalues. So, this transient in fact dies down very soon. Okay. It is like having a large an RL circuit with a large RL. So, that is why you get these two large eigenvalues. The rest of the eigenvalues on the other hand are not very large, they are in fact quite small. And one interesting thing is that if you look at 1 upon Td0 dash, okay, it comes out to be 0.2. So, in fact, one of the eigenvalues is 0.2. Okay. Similarly, 1 by Td0 double dash is 33.33, and you find that the eigenvalue also is minus 33.33. Okay. Similarly, Tq dash and Tq0 double dash. Okay. So, and Tq0 dash and Tq0 double dash. Okay. So, if you look at the eigenvalues, in fact, they are very close or practically equal to the open circuit, the reciprocal of the open circuit time constant. So, let me put this in perspective. When you have a synchronous machine which is under open circuit conditions, the eigenvalues are in fact the reciprocals of the open circuit time constant. In fact, that is why they are called the open circuit time constants. In fact, I waited for a very long time to actually explain this particular point about why they are called open circuit time constants. I hope it is clear now. In fact, the eigenvalues which you get, you can even prove this analytically, we have done it numerically, but the eigenvalues are in fact the reciprocals of the open circuit time constants, which also means that the kind of responses we are going to get are going to be of the kind T upon, I will just write this again in case it was not very clear. You can expect in the response to have, of course, provided that these eigenvalues or modes are observable in the output, you are likely to have responses, especially in the voltage, to contain this and this. In fact, you can also expect, but actually these are not observable in the voltage, these two modes. Okay, these two are. In fact, so that is what we can expect. Okay, this is something you can actually prove. I will not prove it here, but you can prove that these two time constants will be visible in the voltage response. So, if I actually plot time versus Vd, okay. So, I will just interpret this for you in case it is not very clearly visible on your screen. This is 6 e raised to minus 4. So, the 6 into 10 raised to minus 4. So, actually it is 0. In fact, Vd is if you have under, in fact it is showing it to be not exactly 0, because RL we have taken to be a large number which is not infinity. So, it is not a perfectly open circuited condition, but this Vd is extremely extremely small, I am sorry, and it is practically 0. Okay. So, Vd is under open circuit conditions is practically 0 even under transient situations. Okay. In fact, we have proved this about 2 or 3 lectures back, where we had considered the open circuited steady state behavior of the machine. The steady state behavior of the machine is in fact something we did some time back, and we did prove that Vd is equal to 0 and Vq in fact will be equal to EFD, which is the open circuit line to line RMS voltage in steady state. So, the open circuited, so since we have in fact set EFD, or we have given the field voltage so that we will get EFD is equal to 1, we should expect that Vq will settle down to 1. Okay. So, let us just see that, yes it does. Okay. So, it settles down to the value 1, starts from 0, settles down to the value 1, and if you look at this time scale, it is 30 seconds. So, in 30 seconds, it takes about 30 seconds to settle down. In fact, if you see the settling time, it is approximately 30 seconds. The time constant, recall, of the open circuit time constant of a machine can be very large. In fact, here I have taken it 5 seconds. In fact, you can have open circuit time constants of the order of 10 seconds as well. Okay. Then in which case the settling time would be approximately 50 or 60 seconds. Okay. So, I have taken a time constant of 5. So, 5 5s are 25. So, approximately 5 times the time constant is the settling time. Okay. So, this e raised to minus t by Td0 dash is very clearly visible as a slowly increasing, exponentially rising response in Vq. Okay. Of course, from Vd and Vq, assuming that theta is equal to omega 0 t, we can obtain Va as well. So, if I plot Va this is how it looks. Of course, it's a sinusoid. Okay, it reaches sinusoidal steady state. Okay, so it also has the envelope rises in the same way as VQ, but this is sinusoidal. In fact, if I try to zoom this, let's see if I can. Yeah, this is in fact a 50 hertz sinusoid. Okay, since speed is constant. Yeah, so this is a sinusoidal value. I'll just unzoom this. Okay. Of course, you notice that this is tending towards approximately 0.8 and not 1. That's not surprising because we assume that this is a star connected winding, and the line to line voltage, RMS voltage, is 1 per unit. In fact, we have chosen our VF to be such a value so that the line to line RMS voltage is 1 per unit. So one can expect that the phase to the voltage across each winding, which is also the phase to neutral voltage, will be square root of 2 by 3 into 1, which is 0.81. That's why this, you see the peak value of this is going towards 0.8. So you see this going towards 0.8. So this is basically the open circuit response of a generator. Of course, the point is that somebody may ask, well, I'm not seeing the other time constant e raised to minus t by Td0 double dash in this. Actually, Td0 double dash T0 dash is 5 and Td0 double dash is in fact 0.03. So in fact, the reciprocal of 0.03, which is also an eigenvalue as mentioned sometime, is much faster than 1 upon 5. Okay. So that basically the other mode, so to speak, is not visible very clearly, though it does exist. Okay. The reason, of course, being that it dies down much faster than the transient associated with Td0 dash, which is the open circuit time constant. Okay. Now, TQ0 dash and TQ0 double dash related modes are not observable in the response. So this is something I request you to prove that, for this transient in which I take 0 initial conditions. Remember, I am taking 0 initial conditions. If you take 0 initial conditions, you will not see these two terms, this related to TQ0 dash and TQ0 double dash appearing in the response. Okay. So you don't see this for step response. You don't observe this for the step response, but you do see these two. This is not clearly visible because it's very fast. It dies down very fast. I can call this the dominant mode. Okay. So we move on now from this point to the short circuit analysis of a machine. So what we need to do here now is consider that the machine is rotating at a constant speed as we have been doing so far. Then what we do is give a step change in Vf so that you build up voltage. Okay. Once you build up the voltage and it reaches steady state, now give a short circuit to the generator. So what we will do is set RL equal to 0. Okay. So once the machine reaches its steady state, we will assume that we'll take RL equal to 0 suddenly. Okay. Changing RL, of course, changes the value of the state matrix A. That is because A2 changes. Okay. If A2 changes, then A also will change. Okay. So you will find that the state matrix changes and the eigenvalues also change. So the modes of the system, the nature of the modes of the system are different under short circuit conditions as compared to the open circuit conditions. As you may guess, well, there is nothing to guess really. Once you have a short circuit, there will be a current and there will be the voltage, of course, will be 0 at the terminals. Okay. So that is what you will expect to happen. Now what we will do is, of course, we will not simulate the complete open circuit conditions. In fact, we will not re-evaluate the system under open circuit conditions. What we will assume is that we have given this step and the system is now in a steady state corresponding to open circuit conditions. Then after about 5 seconds we will give the short circuit. Okay. So, we will not build up the voltage again, we will assume that it is already built up and the system is in steady state under open circuit conditions running at a constant speed and having EFD as 1 per unit, that is the line to line RMS voltage is 1 per unit. Okay. So, what we need to do is the system we assume, just a moment, we will just scroll back. This is another program, this is not the same program as I showed you some time back. The initial part of the program is the same. We assume that under open circuit conditions RL is a large value. What we do initially is obtain the steady state value of the states for EFT is equal to 1. So, what we will do is assume that the machine is up in steady state, then evaluate the response assuming that the initial conditions are equal to the steady state values. Okay. If we do that, of course, if you are in steady state, remember that the rates of change of the states are 0. So, if we plug in the initial conditions corresponding to the steady state into our expression for the time response, we are just going to remain steady. Okay. So, after some time, of course, this is for around 5 seconds we remain steady at the open circuit conditions. After that we apply a short circuit. Remember, when we apply a short circuit, RL becomes equal to 0. So, that is what is given here. Wonder if it is seen there. Okay. RL is equal to 0, and then we of course re-evaluate A2 and the state matrix. Okay. We re-evaluate the state matrix A, and of course from 5 seconds onwards we use the new A matrix. So, e raised to, what we do is really e raised to the A new from t is equal to 5 seconds onwards. Okay. So, if you look at the analytical expression, suppose you have got the initial condition, rather if you want to express x in x dot is equal to Ax plus Bu, I will just write this again slightly in a large, and you have got the value of x at 5 seconds is given. In that case, x of t after 5 seconds is actually can be written as e raised to a into t minus 5 into x of 5. Okay, plus 5 to t e raised to a t minus tau b into u into d tau. Okay, u of tau into d tau. So, this is basically if you know the initial conditions at 5 seconds and you want to evaluate what happens after at time is equal to 5 seconds onwards. Okay. So, what we will do now is actually evaluate the short circuit conditions. Okay. Okay. So, in fact, if you take out the eigenvalues of A under short circuited conditions, the eigenvalues turn out to be like this. In fact, if you look at the eigenvalues, there is a term here which is minus 3 plus or minus 313.95. This is of course reminiscent of omega, in fact in radians per second. So, if you look at the imaginary part, well, it is reminiscent of that. We will discuss this a bit, this issue, in fact this point a bit further later. The other the other eigenvalues are -2, -34.1, -43.1 and -1.2. In fact, if you look at the time constants, in fact 1 by Td dash 1.2085, in fact the reciprocal of the Td dash is in fact one of the eigenvalues of this system. Okay, 1 by Td double dash is also an eigenvalue. Okay, so the four, in fact the last four eigenvalues are the reciprocals of the time constants Td dash, Td double dash, Tq dash and Tq double dash. Okay, in fact you will expect in the response to see terms like e raised to minus Td dash and e raised to minus Td double dash, and in fact that is why these terms are called the short circuit time constants of the system. Okay, so that is the reason why the time constants are called the short circuit time constants. So if I actually plot VA, or so if I plot VA, initially of course the system is under steady state and under open circuit conditions. At time t is equal to 5, you find that this becomes 0. Okay, so you find that at time t is equal to 5 seconds, the voltage VA for phase A becomes 0. Okay, in fact it becomes 0 for phase B and C also, which I am not showing right now. If you look at VQ also becomes, I am sorry, we will have to close this figure first and I will plot it again. Yeah, so actually it is not seen very clearly. It goes from 1 to 0 at 5 seconds. Okay, so since there is a short circuit, this happens. VQ, in fact, so if you look at VQ, it becomes 0 from 1 at 5 seconds. Okay, so in fact, if you plot IA on the other hand, for example, first what we will do is plot the current ID. If you look at plot of current ID, this is how ID looks like. So it's of course 0 in initially because you are under open circuit conditions, and then there is a big jump. It, in fact, the current becomes a very large negative value, and then slowly it settles down to a value here, which is approximately steady state value is in fact approximately 0.55, okay, whereas so this is the response under short circuit conditions. Okay, so what you notice of course is the response consists of several modes. In fact, some the modes of course are not clearly seen, all of the modes are not very clearly seen, but one of the dramatic things you see is that there is an oscillation. Okay, this is not surprising because one of our eigenvalues is a complex eigenvalue with a imaginary part equal to omega, in fact 313, you recall that eigenvalue? Yeah, so this is what it is manifest here. You also see that there seems to be some kind of a exponential decay. So you know you find an oscillation which decays. So if you just look at me here, you will find that once there is a step, there is an oscillatory value which decays, but also there is a kind of there is another exponential decay here. So there is a decay of this kind and there is a decay of an oscillation as well. So actually this is not very surprising because we are really seeing several modes. It's a response is a superposition of several modes, and the key modes of course in this case are 1 by Td double dash and 1 by Td dash, and of course the oscillatory eigenvalue which we have seen some time back. So there is an oscillatory mode. We'll just get the eigenvalues again. So you can expect to see these things. Okay, I'm sorry. So you are going to get a complex pair of modes. Of course, the whole system is stable because it has got eigenvalues with negative real parts. Okay. So in fact, if you plot IA, which is the phase current, okay, phase current, you will find that we will just redraw this, we will redraw this IA, yeah. So what you see in IA is in fact this is the phase current, remember. In the phase current you see that although in steady state, if you look at things in steady state, it is absolutely symmetric, the waveform is symmetric, it is a symmetric sinusoid as one would expect. In transient, during transients you see a DC offset as well as the envelope of this IA is large. Okay. So what you have as the response of IA, if you look at me, you will find that the envelope of IA decays with time, okay, the envelope of IA decays with time, but also the envelope itself has got a DC offset. So you see a DC offset like this, and you see an envelope which is also dying with time. Okay. So you have a huge envelope in the beginning, that envelope itself decays, and also the envelope is offset and it is coming down like that. Okay. So that is the typical response of the phase currents in case you suddenly short circuit a generator. Okay. So this is what is a typical response of a short circuited synchronous machine. Now, one of the things which we need to, which we can of course see here is that we have done this before. The steady state value of ID is nothing but minus of EFD in steady state divided by XD. You know, this is what one can easily prove for a short circuited generator. In steady state, this I leave this as an exercise, okay, and IQ in steady state is going to be equal to 0. This is something which you can prove very easily. So let us just verify that this is true. So we will just check out that ID, if you look at the value of ID, although there is an initial transient, oh, we will just close this and redo it. Yeah. So the steady state value of ID is approximately minus .55, and if you actually look at EFD is in fact 1. So 1 divided by XD is also 0.55. So what we are seeing is that this, of course, the transient finally becomes the steady state, and in steady state XID is minus EFD by XD dash, XD, I am sorry, it should be XD. Okay. If you look at IQ, the steady state value is 0, does not mean of course that the transients values are 0, and you see this here. You see that there is some transient and this becomes finally 0 in steady state. Now, we move on to trying to understand some other aspects of a short circuited generator. In fact, if you look at the initial value just after the transient has begun, that is just at the time of short circuit, the currents are very large. Okay. If you look at ID or IQ is of course 0, but ID in fact is quite large. You look at this, the steady state value is only 0.55, okay, but if you look at the initial transient, you see the peak value goes right up to minus 8. Okay. So, initially the current is extremely large. Okay. So, this is in fact called a subtransient period, this initial few cycles of the fault just after the short circuit has occurred is called a subtransient period of the machine. In fact, if you look at, you see that the peak value becomes as low as 0.8 and the mean value is approximately, if you look at this figure, the mean value, you can say, since this is an oscillation, I will talk in terms of a mean value, the mean value is approximately -3. In fact, if it's approximately like this. So, if you take out the mean value, something like this. So, if you look at the curve of ID, you will find that it is initially 0 and then it becomes, and then there is an oscillation, the envelope of the oscillation dies down, there is a transient and then it settles down to the steady state value, okay, which is EFD XD. In fact, the mean value of this initial transient, let us call it this, is roughly EFD by XD double dash. So, let us just verify that what we are seeing from this figure here is approximately 3.5, minus 3.5, okay, this is approximately minus 3.5. So, actually let us see what 1 divided by XD double dash is. In fact, this is minus, it is 4.3. This is of course because I can't make out the mean value very easily from this figure. But what you notice is that in the initial period, the current has got an oscillatory component and the mean value is approximately 3 to 4, okay, minus 3 to 4, IDE value is minus 3 to 4. This is because of this, in fact, is the initial behavior just after a short circuit. In fact, just after a short circuit, one can say that the machine currents are determined roughly by the subtransient reactance of the machine. In fact, XD double dash is called the subtransient reactance of the machine. Okay, so the subtransient period, the machine experiences a much larger current compared to what it sees in steady state. In steady state, in fact, the current is 0.55. It is even lower than 1 per unit, the rated current of the machine. Okay, but under subtransient conditions, it can be quite high. Okay. Now, one of the things you will notice in the eigenvalues corresponding to this, we will just see the eigenvalues again. You find that there is a clear separation of eigenvalues. If you look at the eigenvalues, the first two have a very large magnitude. In fact, they have a large magnitude, and this omega, the imaginary part is in fact equal to omega, the rated speed of the machine. It is in fact roughly 340. So, that is the radian frequency corresponding to 50 hertz. Now, it is not surprising, in fact, that the magnitude of it is quite large compared to the other eigenvalues, the magnitude of the first two eigenvalues, the complex pair. So, in fact, can we do a fast and slow state decomposition of this particular system? It is an interesting possibility, right. So, if you look at the state matrix A1, in fact, you have got omega, minus omega and omega here. So, you can guess, I mean it is just a guess, that the eigenvalues corresponding to the first two eigenvalues, in fact, which have got an imaginary component omega, are probably associated very much with the first two variables, that is psi d and psi q. In fact, you can formalize this by looking at the participation factors corresponding to the states, which we discussed this in the first around the 8th or 9th lecture of this course. Okay, so you can actually look at the participation factors corresponding to these eigenvalues, see the participation of various states, but we can guess, we will not get into the complete study of the participation factors, but you can guess that psi d and psi q are primarily associated with this eigenvalues corresponding to the complex pair of eigenvalues, the first two ones. Okay. and that is because just a bit of guesswork. If you look at the state matrix, it has got, in fact, for the first two states, this omega, minus omega and omega in the off diagonal elements, okay, of the first two states. Okay. So, that is just a guess, but it is an interesting exercise to actually prove this formally using participation factors, and I encourage you to really do it. Okay. So, actually an interesting possibility is, of course, to do a simplified analysis and assume that these two states, you set to 0, you have got, in fact, we will call these the fast states, because they are associated with, we guess that they are associated with the eigenvalues of large magnitude, and these in fact are the slower states. Okay. In that case, we can do a fast and slow decomposition, as I had mentioned in the first 10 lectures when we are studying the dynamic analysis of the dynamical systems. We had discussed this issue of fast and slow states, and one of the things I told you, that if you have got a system consisting of fast and slow states, x fast and x slow, then one can actually get the response of the slow states without much error if one assumes that you can set this equal to 0, you set this equal to 0. So, you can in fact express xf in terms of xs, and finally xs dot will be ass minus asf aff inverse afs. So, you can in fact study this system as a lower order system of the slow states. In fact, can we do this in this case? Yes, you can. In fact, I will just run through the code in which I show you that this I just programmed it. We will try to understand it a bit more in detail in the next lecture. I will show you the code for it. I have basically I am doing the simulation of a reduced order system in which I have treated psi d and psi q as fast variables and basically converted the differential equation corresponding to these fast equations into algebraic equations, and then studied a lower order system. Okay. So, I will just look at the code which does this. The same code, what I have done is, oops, we will scroll down. It is the same code except under short circuited conditions. What I do is, I form a reduced A matrix by neglecting the fast transients. Okay. So, this is something I do. So, I call this A old as I just store the old A matrix in A old, and I form the reduced A matrix. This is just a 4 by 4 matrix in the slow variables, which are the variables from states 3 to state 6, that is from psi h, psi f, psi g and psi k, and I do the simulation of this system. Okay. So, I will just slowly go through this code and I will run it once and we will discuss it again in the next class. So, what I am doing is using a reduced order system, okay, to do the simulation. I would not call it a simulation, the evaluation. Okay. So, for example, I can execute this program. This is a modified short circuit program with a reduced order state space by eliminating the state equations corresponding to the psi d and psi q. So, just wait for a while. The eigenvalues of the reduced model are these. In fact, they are not very much different from what we had got earlier from the larger model. So our fast and slow decomposition and simplification does not cause a very large loss of accuracy as far as the slow states are concerned. And of course, if you plot, for example, time versus ID, what you notice is, we'll of course have to, this is the old figure, I will just redo it again. We get a response which is shorn of the oscillatory transient which we had seen earlier. So, we actually get the same response as before, but you initially recall that there was an oscillation of frequency omega b. Now, you do not see it. Okay. We shall use this model in the next lecture. We will just start off the next lecture with this model, with this reduced order model. We will relook at what results we have got, and thereafter we will consider a few more cases of a synchronous machine. Okay. So, with this we stop today's lecture. We have really, this is in fact the first real power system analysis, dynamic analysis we have done in this course using the model which we have developed. So, we will of course continue on this theme in the next class with the reduced order model. Thereafter, we will also in this course go and model a few more elements before we can actually talk in terms of doing an analysis of an integrated system. And mind you, the integrated system, though it will be much more complicated, it is amenable to a sustained and scientific attack, as we have done for the short circuited synchronous generator.